even though you know Bolzano-Weierstrass theorem, to make it complete, I am rewriting here Bolzano-Weierstrass W-E-I-E-R-S-T-R-A-S. Bolzano-Weierstrass theorem. This is every bounded sequence of real numbers has a convergence of sequence. So this is very important result that you are learning. I am not going to write the proof. You have seen the proof in the book. We can discuss every one of the sequence of real numbers as a convergence of sequence. Proof is clear, trivial. You take just write a couple of statements. Let Xn be a bounded sequence of real numbers. To you, this is very important, this theorem, though it is nothing, it is extremely important. In physics, for physics people, this is very important, but they don't know that they are using it. Let Xn be a bounded sequence of real numbers. Then, from previous theorem, it has a monotonic subsequence. Monotonic or monotone. Then the result follows, no? Because if subsequence X and R, if clearly X and R is monotonically increasing, monotonically increasing, co-monotonically decreasing. If X and R is monotonically increasing, since X and R is bounded above, because Xn is bounded above, Xn R converges right? If Xn R is monotonically increasing, since Xn R is bounded above, original sequence Xn is bounded above, so we can do this. Similarly, if Xn R is monotonically decreasing, I will write MD, since Xn R is bounded below, because Xn is bounded below. If Xn R is monotonically decreasing, since Xn R is bounded below, Xn R converges. This completes the proof. So we are using here, the biggest weapon we are using here is every sequence has a monotonic subsequence. That is the strength of this theorem. And this theorem is, because of this theorem we have something called calculus. Some people don't know it. What else? Let's see, I guess. By the way, this has another proof, different proof. I will not prove it that way now. I will give you the idea, because both of you are intelligent, you can understand the idea. Let x and b the boundary sequence. Then having this AB belongs to R such that for each n belongs to n, A less than or equal to x less than or equal to b. I will not be writing the proof, but you can check whether you can write the proof alone. So now the proof is going, all of the xn terms are in this thing. Now you divide this thing into two halves, equal, you bisect it. Then infinitely many extents are here or here. Can be in either one also. Can be in both of them. So assume infinitely many extents are here. So first thing, let's say an is equal to a1 is, no, a, let's say a1 is equal to a, b1 is equal to b. All the extents are in between a1 and b1. Now I bisect this thing. Then infinitely many extents are here or infinitely many extents are here. Assume they are here. Now I am going to do this one. So this is A2, B2. Right? Now A2, B2 is 1/2 of B2 minus A2 is 1/2 of B1 minus A1. Now what is the property here? Infinitely many extents belong here. Now I am going to divide it again. Bisect. Then infinitely many extents are here or here. So assume infinitely many extents are here. So I will draw A3, B3. A3, B3. Infinitely many extents are here. And B3 minus A3 is 1/2 of B1 minus B2 minus A2. B2 minus A2 is 1/4 of B1 minus A1. Right? Now again I am going to bisect it. Then when I bisect, infinitely many extents are here or infinitely many extents are here or in both. Anyway, so I will go to the next one. Let's say assume infinitely many are here. A4, B4. In the interval, closed interval A4, B4, there are infinitely many extents. And B4 minus A4 is 1/8 of B1 minus A1. B1 is actually B, A1 is A. Now again I am going to bisect. Either in this half or this half, infinitely many extents are here. So let's say this side. So I will say then B5, no, A5, B5. So B5 minus A5 is 1/16 B1 minus A1. What is the property? There are infinitely many extents are inside. So I am going to continue this way without quitting. So I will get a sequence of closed and bounded intervals, infinitely many extents are in that interval, regardless of how small it is. Regardless of how small it is. So let me do one more. Say this one. Very small. A6, B6. Right? Then there are infinitely many extents are here. Now can you see B1, B2, B3, B4, B5, B6 decreasing sequence and bounded below by A1 or A. A1, A2, A3, A4 and the same. A5, A6 increasing. Right? And Bn minus An is 1/2 to the power n minus 1, I guess.
Yes.
B1 minus A1, no? Since Bn is monotonically decreasing and bounded below, it converges. Since An is monotonically increasing and bounded above, it converges. However, Bn minus An limit is when n tends to infinity, you have 1/2 to the n minus 1
Is equal to 0.
equal to 0. Therefore, limit of B and limit of An,
Must be equal.
they are equal. Now, if you take, for instance, x1 from this interval, x2 from this interval, x3 from this interval, x4 from this interval, x5 from this interval. So what will happen is xn is in between Bn and An, limit of An, limit of Bn. There are infinitely many. I am picking one. Axiom of choice or something. Let's not be that serious. So you can pick a one for every n, An less than or equal to xn less than or equal to Bn. Some xn, not exactly xn, some xnk or something like that. Limit of An converges, Bn converges to the same thing. Therefore, this one also converges to the same thing. That is another proof. This is called nested interval. Nested interval theorem or something like that. So that is the proof. So very important that you continue. At least one of the intervals has to have infinitely many extents continuously. So that is another proof. Both proofs are very down to earth. There is nothing we have assumed. Nothing. Understand the proof, no?
Yes.
We can write it down precisely. But no need to write now. Now we are going to discuss limb sup and limb mean. So I guess I have 1 hour here, next day 3 hours, can finish. I will write everything, but without writing proofs. Whenever necessary, I will write the proofs. Nested interval theorem is used in analysis quite a lot. Quite a lot. Let's see in the meantime whether my wife is called. Sometimes my phone. We are going to come to Limsup and Lim for me. I have here, I will write every proposition, then you can see how it goes without writing the proof. Because we have only 4 hours to do everything. Let me say, let Xn be a bounded sequence. Bounded sequence by Bolzano-Weierstrass theorem. Weierstrass, W-E-I-E-R-S-T-R-A-S. By Bolzano-Weierstrass theorem. Lxn is non-empty. Right? Because every bounded, we discussed on Bolzano's theorem. Since it is bounded, it has a convergence subsequence. Lxn is set of all subsequential limits. So Lxn is non-empty. First proposition. Let Xn be bounded. Then who? No, then Lxn is bounded. Clear, no? Since Xn is bounded, Xn is in between some two numbers A and B. Therefore, any Xnr is also between A and B. Therefore, limit Xnr is in between A and B. That means any L is between A and B. Right? You don't want me to write precisely, no? Lxn is bounded. That's a very important result. So you have seen this by many examples. And if you take a convergent sequence, if Xn converges to X, then Lxn is singleton X. This is clear, no? Because every subsequence converges to the same X. Now you have computed Lxn for Y, number of very easy, for very easy sequences, simple sequences. This is the theorem. Let Xn be about is already given. Then lim sup xn is equal to maximum of Lxn and lim inf xn is minimum of Lxn. So that is a very strong result. Ls, all we know is Lxn is bounded and unempty. Bounded and unempty. I am saying lim sup xn is the maximum of Lxn, lim inf xn is the minimum of Lxn. So this is a very, very strong result. Because just because of xn is bounded and unempty, you cannot say it has a max and you cannot say it has a min. All you can say is it has a sup and it has an inf. But I am claiming more than that. So this lim sup xn is max Lxn, lim inf xn is min Lxn. What this says is that there is a subsequence of xn which converges to maximum of Lxn. Similarly for the lim inf, it has max and min. I don't know whether I should prove it, not today because I want to give you the idea, but this is a very, very strong result. I remember in his approach also he did some kind of claim. It is not clear somehow. It is not clear because when you write Lxn, it will not be an open interval type thing. Always it has a maximum as well as a minimum. So proof is kind of somewhat long, I have written. I will not present it today, but I have to before the course lecture is over. So then the story is what? If you are given the bounded sequence, if you get the set of all subsequential limits, that set is bounded, not only bounded, that set has a maximum and a minimum, and that maximum is called lim sup, and that minimum is called lim inf. So this is a very powerful result, even in this book. I mean, this is what I have written now. It is a very long proof, not very one-page proof. Proof is interesting. That's why I say hereafter, you can say, if somebody asks you lim sup, what is lim sup? Let's talk about, so far we have talked about unbounded sequences. We are talking only bounded sequence for the time being. If you take a bounded sequence xn, if you collect all the subsequential limits, it has a maximum. That maximum is the lim sup. That set has a minimum. That is the lim inf. Actually, nowadays I am writing for the 8th A-level people. It's over, but I am extending the book to university level. I write these things for very simple examples of sequences, so that they can get the idea of lim sup. I mean, from the book style is not clear now, because what book does is x1, x2, x3, x4, x5, x6, x7, x8. What he does is, he considered that he begins from say x2, get the sup, begins from x3, get the sup, and it is a decreasing sequence. No, that sequence has actually decreasing and bounded below. If if we start from a bounded sequence that has a limit, he says that is the limb sup. It is very artificial because you are considering this supremum of x n plus 1, x n plus 2, x n plus 3, and so on. Supremum of this thing, you take the supremum of this thing, then you take the limit. There is something good about it, however, when you, because of limb sup, here you have limb sup, supremum of limit of the supremum's limb sup. Similarly, limit of the infimum is limit. In that sense, it is good, but idea-wise, if you are asked by somebody what is the limb sup, you cannot give this one. What I am saying is much clear, very much clear. What I am saying is, when you are given any sequence, it has a monotonic subsequence. Therefore, by Bolzano-Weierstrass theorem, it has a convergent subsequence. So you can say that set of all subsequential limits, it is non-empty and bounded. There is a theorem, this theorem, that I have to prove, not today, but by next, I guess, next Tuesday, not Tuesday, next Wednesday also. Set of all subsequential limits has a maximum is called limb sup, minimum is called limit. Even for an engineering student, that definition is workable now. This one is not clear. You are taking, you cut from somewhere, consider all the elements, set of all x n greater than or equal to some number, take the sup, take the limit. That is true. So advantage of that thing is it works with the word limb sup, limit of sups is limb sup, limit of inf is lim inf. So that is the definition of limb sup, and you got it, no? If somebody asks you what is limb sup, you know what it is. You don't need to, this is correct, but you cannot just say it. The way I am saying is very clear. You get the sequence, xn, you take all the subsequential limits. It has a maximum, that maximum is limb sup. It has a minimum, that thing is limit. So, it is so much of epsilon type stuff. As a result, I am not writing the proof today, but no, not enough time, because I want to, certain things without a proof, I want to tell you, because you need to have the idea. Then, here this is for a bounded sequence, no? For a bounded sequence, this is how you define limb sup and limb min. Even if you take an unbounded sequence, if it is unbounded above, it has a sequence, diverges to infinity. No? If a sequence, you can prove it, no? Yes, is it a homework problem? Oh. But you can prove it, no? If a sequence is unbounded above, it has a subsequence that diverges to infinity, and if you, the sequence is unbounded below, oh. So this story is for a bounded sequence, and if a sequence is unbounded above, it has a subsequence that diverges to plus infinity. Therefore, by this definition, Lxn has to contain infinity. Right? Therefore, limb sup xn will be infinity, plus infinity. If a sequence is bounded below, if a sequence is unbounded below, that sequence has a subsequence that diverges to minus infinity. So by the definition of lim inf of that sequence will be minus infinity. I have discussed, without saying, I have discussed there are sequences bounded above that does not diverge to minus infinity. There are sequences bounded above, if you take say minus n, it is bounded above, but it diverges to minus infinity. But there are sequences, you can write so many, I can unbounded above, but does not diverge to minus infinity. Then it has a subsequence which is bounded. Let's prove that today. Now, anyway, my way of defining, this is how I have defined lim-sup. It is, this way you can tell anybody the meaning of lim-sup, of a bounded sequence or even unbounded. Lxn always has a maximum and a minimum. That maximum is called lim-sup, and that minimum is called lim-min. So here is a very strong statement, max and min. Just because of bounded above and below, you cannot say maximum is there. But so I have to write the proof. I must get ready for next Wednesday, to prove it for you. This is terribly epsilon. So let me erase this thing. Let's prove this theorem, Theorem. Let Xn be a bounded above sequence. That does not diverge to minus infinity. Minus infinity. Then there exists a sequence. Xn of Xn. That is bounded. If a sequence is bounded above, and if it does not go to minus infinity, then it has a subsequence that is bounded. Okay, proof. Let us write the proof. Since Xn diverges to minus infinity, if Xn diverges to minus infinity, then for each capital N greater than 0, there exists n belongs to Z plus such that for each n greater than capital N, Xn is strictly less than minus n. That is the meaning of diverges to minus. Thus, if xn does not diverge to it, doesn't diverge, does not diverge to minus infinity, but
there exists capital N greater than 0
there exists capital N greater than 0
such that for each n belongs to Z plus capital N belongs to Z plus
for each n belongs to Z plus,
there exists simple n greater than n
does that
simple x simple n is strictly greater than or equal to minus.
very good. Putta, you agree, no? So I am going to write the same thing here. Since xn does not diverge to minus infinity, there exists capital N greater than 0 such that for each simple n belongs to Z plus, there exists n belongs to Z plus such that n greater than nn, xn greater than or equal to minus 1. Yes? Right. Then there exists n1 belongs to Z plus such that n1 greater than 1 and xn1 less than greater than or equal to minus 6. No, same like. Then there exists n2 belongs to Z plus such that n2 greater than n1 and xn2 greater than or equal to minus n, right? Because if I choose n1, we have to have some, that's what this one is, no? They are n greater than 0 properties that no matter what n you consider from Z plus, there is an integer n greater than capital N such that xn greater than or equal to n. Something missing. Since xn does not diverge to r xn greater than 0 for xn belongs to r xn. Okay. Now n2 greater than n1 and xn2 greater than or equal to minus n. And proceeding in this manner, it can be shown that if you are writing a rigorous proof, you have to use induction then. Unnecessary here, proceeding in this manner, it can be shown that there exists a strictly increasing sequence of integers. Array is strictly increasing sequence of positive numbers, positive say integers, is strictly increasing sequence of positive. In R or in A, whatever, it doesn't matter what you write. Of proceeding in this manner, it can be shown that the array is the strictly increasing sequence of positive integers in R such that x in R greater than or equal to minus n for each R belongs to Z plus. Since you are playing election zone, then there are research substitution or everything that is bounded. Anyway, since xn is bounded, can you see the main thing in this proof is writing the negation of that line only. Many theorems are like that. So that's why you need to be very good at logic. So simple. Since xn is bounded above, xn R is since xn is bounded above, there is, let's see, there exists some B belongs to R such that for each n belongs to n, xn less than or equal to B because it is bounded above. Thus, for each R belongs to Z plus minus m less than or equal to xn R less than or equal to B. So I have proved if the sequence is bounded above and that does not diverge to minus infinity, then there exists a subsequence xn R of xn that is bounded. I have proved it. So, in order to define limits of, we need this one. Proof, not theorem. Let xn be bounded, let xn be bounded above say by B, the sequence, let xn be bounded above sequence that does not diverge to minus infinity, then lim sub xn is a real number. If it is bounded above and if it does not diverge to minus infinity, then lim sub xn is a real number. Proof is again not a big deal, but can you see all of them here? We are not using any high machinery at all. Nothing like that. this thus logical arguments. Ability to write the negation of a statement is essential here. I want to prove this one also. Proof. Whatever by definition, lim sub xn is sub over max whatever L is n tends to infinity. Lxn. From previous theorem, we know that there is a subsequence subsequence x is R of xn. There is a subsequence, bounded subsequence. X in R of x in R of x n. Then it follows from Bolzano-Weierstrass theorem. Then it follows from Bolzano-Weierstrass theorem that there are further subsequences from the further subsequences of the boundary sequence. X in R, it is a very clear statement that converge. From here, from previous theorem, we know that there is a bounded sequence. You have the original sequence xn is bounded above. It does not diverge to minus infinity. As a result, it has at least one bounded subsequence. Then I am saying then it follows from Bolzano-Weierstrass theorem that there are further subsequences of bounded sequence x and R that converge. No? Bolzano-Weierstrass theorem said every bounded sequence has a convergent subsequence. Because x and R is bounded, it has further subsequences which converge. Then it follows that the limits of these further subsequences are real numbers less than or equal to b. So this is bounded above. Less than or equal to b. Hence Lxn is necessarily subset of minus infinity b, because of this thing. Hence minus infinity is strictly less than lim sub xn less than or equal to b. Right? So what I have shown is that, of course, if you take examples, this works right away, but this example is not a proof, no? What I am saying is, if xn is a bounded above sequence that does not diverge to minus infinity, is lim sub. Is because it is bounded above that does not diverge to minus infinity, it has a bounded subsequence, no? Since it is bounded, its subsequence by Bolzano-Weierstrass theorem, it has convergent subsequences. So their limits are again bounded above by b. So these are bounded, it cannot go to negative infinity. No way, therefore supremum of the set is less than or equal to b. So that is very important. Similarly, you can do that, because the reason I am doing this thing is we have to discuss lim sub and lim inf of any sequence. What I am saying here is, if it is bounded above, if it does not diverge to minus infinity, lim sub is a real number. Similarly, you can write xn be bounded below sequence that does not diverge to plus infinity. Then lim inf is a real number. Same proof works. Same proof. Only thing is you change the order other way around. That's all you do. So then we are, I guess done with, if you take a sequence, if it is divergent to minus infinity, we have to say lim sub is infinity. If that diverges to minus infinity, if xn is special unbounded below. Reason here, what I want to show is that if you take a sequence xn, if it can be bounded, if it is bounded, lim sub, lim inf, all are real numbers. Because according to my definition, I didn't prove maximum of subsequential limits is the lim sub, minimum of subsequential limits is the lim inf. Now, when you take this kind of sequence, it is bounded above, but not does not bounded below, because you can apply the result true for bounded sequences. If it does not diverge to minus infinity, maybe it is like something like this. You take a sequence, xn, see, maybe it is going like this. You go here, it will not, no matter how far you go down, it has to come up, since it does not go to minus infinity. That is why in a sequence like this, lim sub is going to be a real number. However, if xn diverges to minus infinity, then we define, I'm not writing everything by the way. If it is diverging to minus infinity, then lim inf is, because if it diverges to minus infinity, every subsequence diverges to minus infinity. Therefore, lim inf must be, lim sub lim means both must be minus infinity. Similarly for lim sub and which are diverging to plus infinity. Again, I guess that is the thing you need to know about the idea of lim sup and lim inf. Then you are not taking as, of course you know that the way book defines is correct, but it's not close to your heart. When you say, you take any set xn, any sequence xn, then if it is bounded, especially by Bolzano-Weierstrass theorem, it has convergent subsequences, then Lxn is non-empty as a result. Then here I said we have a proof that I did not prove today because I want to give you the idea first. And the proof is kind of long, but very important that you know how to do it. So I am giving you the idea only here. Somebody asks you what is lim sup maximum of the subsequential limits. Funny thing is, if you take a sequence xn, it may not converge. It has many. I will take away my word converge. It may not have a limit. You are given a sequence, it may not have a limit, but it may have so many subsequences which have limits. Some limits can be minus infinity. Some can be plus infinity. Some may be one subsequence which convergent to 3. For instance, if you write a sequence, first one is 1, second term is minus 1, third term is 3, then 2 minus 2, 3, 3 minus 3, 3, 4 minus 4, 3, 5 minus 5, 3, 6 minus 6, 3. This sequence, one set of numbers, one subsequence of numbers diverging to plus infinity, some diverging to minus infinity, some is actually constant sequence 3. So that is the thing you need to know. However, for a bounded sequence, lim sup is the maximum of what? Maximum of subsequential limits. Now you got the idea. Now we have to prove that result that we used to, that his theorem in the yellow book, I mean you know it but not enough. Not enough, let's see. Let's leave it over there. Very important. Let xn be a sequence of real numbers. Real numbers and lambda becomes Schwarz. Lambda is a real number again, that's what it means. Then lim sub xn equals lambda. If and only if, let me write this. If and only if for it epsilon greater than 0, there exists n epsilon belongs to Z plus such that for each n greater than n epsilon, xn is strictly less than lambda plus epsilon. I draw this picture from the book. This is not how he said it without using epsilon, but the idea was same. And for each m belongs to n, Z plus, there exists n belongs to Z plus such that n greater than m and x for each m belongs to there is n, xn greater than lambda minus epsilon. I mean, he did not use epsilon language.
He used x.
Yeah, he used some x, that kind of thing. Because I am an analyst person, so I want students to be familiar with the epsilon thing, otherwise you cannot do anything in analysis. Let us, you should prove both actually. What he says is lim sub is lambda, here is lambda, somebody give you epsilon, positive. Here is lambda plus epsilon, here is lambda minus epsilon. So what is this? Somewhere here you have n epsilon, graph is below here always. But it cannot be here all the way. It has to come above this line, once in a way. That's what it says. First line says, after n epsilon it is below lambda plus epsilon. But if you take any integer, n, any integer for m, if you take any m somewhere here, there must be a place bigger value, bigger than n bigger than m, such that it goes above this line. So that is the, this is what you will be using when you are doing analysis to prove limits of this one. What he said is true, but that is kind of difficult for a student to handle without epsilon, even though it is true. So we need to prove this thing, and actually we need to prove the other one also. Let's be a sequence of real numbers, and mu belongs to R, then lim inf xn equals mu if and only if for each epsilon greater than 0, there exists n epsilon belongs to Z plus such that for each n greater than n epsilon, xn greater than mu minus epsilon. Other way. And for each n belongs to Z plus, there exists n belongs to Z plus such that n greater than m and xn less than lambda plus epsilon. Other way around. This is lim sub, no? This is lim sub. Graph of lim sub. Graph of lim inf is the same thing. Here you have say mu. This is your mu. Then this is mu plus epsilon. This is mu minus epsilon. So this is mu plus epsilon, this is mu minus epsilon. So you are n epsilon, after n epsilon, it is always above here. But it cannot go all the way to New York or heaven. It has to come back this line once in a way. That is the picture. Now, if you get this picture and this picture both, lambda and mu are the same, then you can see both happens when lambda, if lambda is equal to mu, you can see it is the limit. So by the picture, it follows. Let's see whether I can do this thing. I want quickly. I cannot postpone everything for next day. However, proof of this thing is very important. Proof of the theorem that I didn't prove maximum minimum, that also you need to see this one. Maybe I will prove this one only lim inf one, then you may be able to prove it. So I have, I guess, not enough time. I don't want to stuff on the way. On the way. Kind of long. Then next theorem is about lim inf, and they are the most important things. And here I have so many exercises. We need to have the ideas. Then actually I have proved that result also. Let Xn be a bounded above sequence that does not diverge to minus infinity. Then lim sub Xn is limit n tends to infinity sub xk k greater than n. That is the result. Let's see, at least I should prove that, I guess. Yeah. I have wrote them very, very clearly here. Let Xn be a bounded below sequence that does not diverge to plus infinity. Then lim inf Xn is, and let us prove one of them. So, this is this theorem. I owe you the proof, and the previous Max-Min theorem, I will owe you the proof, otherwise your knowledge will be somewhat shaky. So let's prove this one at least. No, I guess enough time, I think. This result. I think now by now you have somewhat good idea about lim sub and lim inf. In analysis, quite often you need this lim sub and lim inf in measure theory that you will be studying, because the advantage here is, can you see, if you are given a sequence Xn, you cannot write no lim Xn, but you can always talk about lim sub Xn and lim inf Xn. That is the biggest advantage. So when you want to see something is has a limit, well, this is, you are given the sequence, you say consider lim sub, consider lim inf. By doing this and that, eventually you do they are equal in measure theory, and some of the measure theory. I then remember, and I don't want to write it also because you are not going to use it now. You go over there. Let's see whether we have time to do theory. Because now, because you have introduced lim sub in two different ways, no? But I want you to see that both are the same. Let Xn be bounded above sequence. that does not diverge to minus infinity, then limits of xn is limit of and supremum of set of all xk k greater than n. Let's do that. In the other book, this is the definition. Now we are going to prove it. Because book method is sort of artificial. Here, this way is you take a sequence without knowing any theorem, you can compute the limits of this way very easily. Okay, let's prove this proof. Let lambda is equal to limits of xn. We can always, can you see the advantage? You cannot write let lambda equals lim n xn. Cannot write. You can write this. As before, I mean not as before, let I am referring to other things in capital equals m n, what did I use? M n is the supremum of let m n is equal to supremum of set of all xk k greater than n. M n is equal to this thing. Let L belongs to Lsn. Then there is a subsequence. There exists subsequence xn xjr I have written, I don't know why there x br of xn such that limit r tends to infinity x br is equal to L. I want to ask a question, by the way. Some of the lecturers, they come and they write proofs, they say I have proved it. Students don't know anything. Am I doing the same thing?
No.
They have, must be my wife.